our next speaker is, an absolutely phenomenal student of the great Jamie Matthews, and she has been doing some remarkable work with. She's a big deal here in British Columbia. I'm sure she's a big deal across Canada. She's been doing some remarkable work with the Kepler Space Telescope data, and she's actually she's discovered several planets that the Kepler scientists did not discover in their data, which is so cool. So anyway, I am going to turn everything over to Michelle Kunimoto.
Just getting set up here. I'll share my screen. All right, how's that looking for everybody?
That looks good.
Okay, well, thank you for having me on here today. I'll be talking about what it means to find other Earths elsewhere in the galaxy. I'll also talk a little bit about the research that I've done as a student at the University of British Columbia, and what anyone listening to this presentation can actually do to find planets as well. So to start off, I actually want to harken back to the original series of Star Trek, because this is actually what inspired me to go into astronomy. As they say in the show, the mission of the Enterprise was to seek out new life and new civilizations and boldly go where no one has gone before. And I really think this message instilled a strong sense of curiosity in me and a desire to learn more about the universe that we live in. I'm sure many of us have asked ourselves the age-old question of, are we alone? Which is not just a scientifically fascinating question, but also philosophical. And if there is other life out there, where might it be? What kind of planets could life exist on? Are there other planets out there that look just like our own Earth? So by finding other planets, especially those that could be considered habitable, I feel like we can start to answer these kinds of questions and more. Now, these other planets that I'm talking about are known as exoplanets. Exo means outer, so an exoplanet is a planet outside of the solar system. What searching for exoplanets has revealed is that planets are a lot more diverse than what we see in our own solar system. Just as a few examples, there are examples of super Earths, which are planets, rocky planets that are larger than our own Earth. Astronomers are very well known for their creative naming conventions. We also have sub-Neptunes, which, as you may have guessed, are similar to Neptune, but smaller. And what's really interesting already is that super Earths and sub-Neptunes are among the most common types of planets that we've found so far, yet we don't actually have any of these in our own solar system. So this is a really important question to already start to ask. There are also examples of hot Jupiters, which are these really exotic planets, giant planets that orbit so close to their stars that they're extremely hot. Again, totally unlike what we see in our solar system, where all the giant planets are far away from the star, our sun, and all the small planets are close. There are also what I lovingly refer to as Tatooine worlds. So these are going to be planets that don't just orbit a single star, but multiple stars, for instance, in binary or trinary star systems. So the Star Wars fans listening here can probably think of Luke Skywalker's homeworld, Tatooine, as an example of this in science fiction. But what specifically makes a planet considered habitable? I'll be covering a few of the basic criteria, just the kinds of things that planet hunters keep in mind when answering this question. Now, as a caveat, I do want to emphasize that this is taking a very Earth-centric view, and we're going to work under the assumption that a potentially habitable planet should have qualities similar to the Earth. Just for example, that life is going to need water to survive, but there's always going to be a lot of questions about whether this is actually the case. But without further ado, first, the size of a planet is going to be really important. We want to make sure that it's small enough that it's rocky like our own Earth, compared to the large planets, which are going to be gaseous. But we don't want it to be too small, because it might be something like Mars or our moon, where it has too low of a mass to be able to support an atmosphere. So if I were to put some just approximate broad numbers down, let's consider a potentially habitable planet has to have a radius between 0.5 and 1.5 times the size of Earth. We also want to make sure that our planet has a temperature that can support liquid water, because we believe water is a requirement for life to survive. So this is known as orbiting in the habitable zone of its star. This is the range of distances from a star where a planet can orbit and have liquid water on its surface. So that means it's not so hot that any liquid water would boil away, not too cold that any liquid water would only be able to exist as ice, but just right for liquid water to exist. So if some of you might be thinking of the Goldilocks story, Goldilocks and the Three Bears, and that's exactly right. This habitable zone is actually also referred to as the Goldilocks zone. Lastly, we also want to make sure that our planet orbits a star that's similar to our sun or smaller. When we get to the really big and hot stars, they go through their fuel extremely quickly, so they don't live very long. And we want to make sure that a planet is going to survive long enough that it will be able to let the life on it develop. And this could take billions of years. So we want to make sure a star can live that long. On the other hand, we have really small, cool stars that have nice long lifetimes. They're also among the most common types of stars in our galaxy, which makes them favorable topics to really understand the potential for life. But unfortunately, because these stars are so cool, any planets in the habitable zone have to orbit very close to those stars just to have a high enough temperature to support water. And that means that they're going to be bombarded by a lot more radiation than what we're used to here. They could also be tidally locked, which means that one side of the planet will always be facing that star. So you'll have that side being really hot and the opposite side extremely cold. That being said, these qualities don't necessarily preclude small stars from hosting potentially habitable planets. In fact, there's a lot of studies right now that are trying to answer the question of, is a lot of excess radiation necessarily a deterrent for life, or can there be things like extremophiles that can exist on these kinds of planets? And then, of course, there's the sun-like stars, which are somewhere in between these two. These are going to be ideal for finding the closest Earth 2.0. And of course, we are living proof that it is possible that life can exist around these stars. So in summary, we want to make sure that a potentially habitable planet has a size of roughly 0.5 to 1.5 times the size of the Earth. We want to make sure that its temperature can support liquid water, so it orbits in the habitable zone of its star, and the host star that it orbits around will be similar to the sun or smaller. So now that we know what defines a potentially habitable planet, how do we go about finding them? Well, one thing it might surprise you to know is that it wasn't until about 30 years ago that we actually found the first exoplanet. In fact, the 20th century view of known planets was pretty accurate for thousands of years. I mean, some of the planets in our own solar system we'd known about for thousands of years because they're visible with the naked eye. And some of them we were able to see over the past 100 years with backyard telescopes. But it wasn't until around the 1950s when candidates for exoplanets began making their way to popular press. All of them turned out to be flukes in the data, and technology was simply not there yet to find exoplanets. And it wasn't until the first confirmed discovery in 1992 that the first exoplanet was found. So this is actually a very fast-growing and young science. Now, there are a lot of different detection methods. I won't be able to go into every one, but I do want to focus on the one that I used and the one that is the most successful detection method to date. So this is known as the transit method. So the basic idea is that an object passing in front of a star will block a portion of that star's light and cause a temporary decrease in the brightness of that star. So as you can see here, there's that little object blocking the light and causing a transit. So if these dips happen periodically, it's a really good sign that what you found is a planet orbiting in front of that star and periodically blocking it as it orbits. The good thing about the transit method is that it's actually the only method so far that can give us an estimate of the size of a planet, because the depth of the transit gives an estimate of the planet's radius relative to the size of the star. Of course, a larger planet will cause a greater transit, a deeper transit, and a smaller planet will cause a very shallow transit. There are a few downsides to the transit method. One is that there are a lot of common signals that can mimic a planet signal. So it might not be a planet that you found, but actually a very low mass star that's instead blocking the light. Or it could be an eclipsing binary that just grazes your target star and blocks a little bit of its light. So there are some different things you have to be careful of. Another thing is that there's only a very specific orbital orientation that can allow you to actually see a transit, because the planet basically has to pass directly in between the Earth and the star. Now, this is a very low probability of happening, Just as an example, if you're an alien observer trying to see the Earth transit the sun, the probability that the orbits are going to be just so aligned that you can see that will be less than 0.5%. So this means you're going to need to observe hundreds of hundreds of stars just to have a small chance of finding only a few planets. So this is a plot of planet mass and orbital period, just showing kind of the earliest detections of planets. So maybe the first 2 decades of planets. And what we were finding is that most of the planets were larger than Neptune. In fact, 85% of the planets in this plot are more massive than Neptune. We're also finding a lot of these examples of hot Jupiters, which, as I mentioned before, are giant planets that are very hot because they're in extremely close in orbits. So the early picture of the exoplanet population was so far very different from what we are familiar with in our own solar system, and there were a total lack of small planets. The reason for this is really just that the technology wasn't there yet to be able to find small planets like those that are similar to the size of the Earth around sun-like stars. But all of that changed with the Kepler mission. So Kepler was NASA's first exoplanet finding mission, and it was the first mission capable of finding Earth-sized planets in the habitable zones of sun-like stars. Now, in order to achieve this, Kepler needed to be able to detect a change of brightness a change in the star's brightness on the order of 10 parts per million, or 0.001% change in brightness. So just to give you a bit of context for what this means, I want you to imagine the Empire State Building, and it's dead of night, all the lights are on, all the window shades are up. Somebody closes the shades of just a single window by a few inches, and you need to detect the change of brightness from 100 kilometers away. Now consider that a transit might only last a few hours, and it might only happen once a year or once every 10 years. So you're going to need to look at a star continuously for years just to be able to have a chance at seeing a single transit of an Earth-like planet around a sun-like star. So that's basically what Kepler did. They observed 150,000 stars simultaneously and continuously, taking data every 30 minutes for 4 years. The reason they had to observe such a large number of stars was because, as I mentioned, the probability of seeing a transit is so low. In case planets were really rare, you're going to need to observe hundreds of thousands of stars just to hopefully be able to find a few thousand planets and get some really good demographics. So this is that plot I showed you before of the early exoplanet detection. So this is pre-Kepler, which was after Kepler launched in 2009. They've since released a lot of catalogs, and as you can see, it totally revolutionized our perspective of the average planet in the galaxy. So thanks to Kepler, we now know that small planets are extremely common, and in fact, the most common types of planets seem to be those between the sizes of Earth and Neptune that we found so far. In terms of this morning, I've just updated these numbers, and we so far know of over 4,000 confirmed exoplanets, and Kepler has confirmed over half of those. So just to give you an idea of how revolutionary Kepler was. And Kepler also has more than 2,000 planets that are still waiting to be confirmed. Based on the number of stars in our galaxy, there are hundreds of billions of planets out there. Kepler has so far confirmed 31 planets in the habitable zones of their stars, and those that are considered small. Of these, I would say the closest Earth analog so far, the closest Earth 2.0 would be Kepler 452b. So this planet has a year of 385 days compared to Earth's of 365 days. And it's actually the only small planet in the habitable zone that orbits the same type of star as our own sun. Initial estimates placed the radius of this planet at about 1.6 times the size of Earth, although reanalysis has actually placed it closer to 1.1 times the size of the Earth. So this is definitely the closest Earth analog so far, and it will be really fascinating to do follow-up research to better characterize it in the future. So this brings me to my own experience with Kepler data. When I was in my 3rd year of my undergraduate degree, I took a course called Exoplanets and Astrobiology at UBC, taught by Professor Jamie Matthews. And this was actually the first time that I'd ever learned about exoplanets and how to find them, other than what little I knew from watching Star Trek. And I asked Professor Matthews at the end of the term about the possibility of working on an exoplanet or habitability related project just for a summer research project. For that project, I was tasked with looking through Kepler data to see anything that might have been missed by the official team or other independent searches. And that work turned into my undergraduate honors thesis and eventually into my dissertation as a PhD student. And really, it's why I'm here talking to you today about finding other Earths. So one of the great things about Kepler is that all of its data is available to the public. So my search process started out with downloading all this data just online. And this was in the form of light curves, which are measurements of the brightness of stars over time. For my undergraduate work, I looked at 400 light curves, and for my PhD work, I actually reviewed the entire 200,000 star set from Kepler. Then I would pass each of the light curves through a search routine that would automatically look for signs of transits. This is just an example of some real data that I would find. You can see that a typical planet transit has a really nice U shape. It looks consistent. This is going to be one of the more obvious ones, of course, that Kepler would already have found, and I was looking for ones that they had missed. So after finding a whole list of these kinds of signals, as I mentioned before, there could be some that aren't actually planets, but are caused by stars, or it could just be random fluctuations in the data that coincidentally looks like a transit. So you do have to be careful that what you found is a planet. So I would pass these through different candidacy tests to assess each signal and spit out a list of planets that would be my best planet candidates. So as an undergraduate, I found 4 new planet candidates through this process, and as a PhD student, I added another 17 for a total of 21 new planet candidates. And as a PhD student, because I was looking at the entire set, I actually rediscovered thousands of the Kepler planets that were already known. I actually had a 99% recovery rate of the confirmed planets that were found by Kepler. So I won't have time to go through every single new planet, but there are a few that I am more excited about than the others. One of them is KOI 205.02. This planet is Mercury-sized, which is actually one of the smallest planets to be found with Kepler so far. This big one here is KOI 408.05. It's what I've dubbed a warm Neptune because it's slightly larger than Neptune, but is actually in the habitable zone of its star. And the one that I'm most excited about is this one with the long name here, I won't read. It is 1.5 times the Earth size, and it is in the habitable zone of its star. So as I mentioned before, using that criteria of a potentially habitable planet, this one is definitely a significant discovery that I'd be really interested in following up in the future. That being said, this planet is thousands of light years away. We're not getting there anytime soon. It's going to be difficult to do some follow-up work on it, but finding more examples of these kinds of planets helps us estimate how common these planets are. So even if I can't do anything more with this planet, at least it can contribute to some really interesting statistics. So that brings me to the point of how anybody listening here today can actually start looking for planets as well. As I mentioned, all of Kepler's data is available to the public. You just have to have an internet connection and be able to go to this website to download all this data. And there's also a lot of online resources for finding and analyzing transit signals. And a lot of the missions from Kepler and more recent ones are really encouraging people from the general exoplanet community and even the general public to participate in finding planets. I would say that Kepler has been pretty well searched at this point, but there's several other missions, particularly K2 and TESS, which have also released their data for the public to use, and there's a lot more things that can be found there. In particular, Jason Rowe was on the original Kepler team, and he was immensely helpful in teaching me how to look for planets when I started as an undergraduate. So he's actually released all of his transit search and analysis code to the public on GitHub. There's tutorials, examples. It was really, really useful. So if anybody is keen and wants to try this, I would really recommend that's a good place to start. Another option is the Planet Hunters project, which is based on the idea that humans have a remarkable ability of pattern recognition and can spot what computer algorithms might actually miss. So what you can do is just go on their website and look at the light curves yourself with your own eyes. and just try to find different signs of transits or even really strange and unique events that would be ignored by a planet search algorithm. Planet hunters have actually found more than 100 Kepler candidates. Again, these are just discoveries made by amateur astronomers and those in the general public, and they're actively working on the data from more recent missions as well. So on that note, I would say that the future of planet hunting is very, very bright and exciting. Kepler has kind of opened up the floodgates for finding small Earth-sized planets, and exoplanets are a really hot topic in astronomy right now. There's a lot of major missions that are currently in operation or planned over the next decade, so I'll just review a few of those. There's TESS, which launched in April 2018 and is NASA's current exoplanet finding mission, where Kepler looked at a single patch of the sky to observe the same 200,000 stars simultaneously. TESS instead is actually the first spaceborne all-sky exoplanet survey, so it's monitoring 200,000 nearby bright stars. One of the good things about TESS is that because it's observing nearby bright stars, those stars are going to be a lot more amenable to follow-up with other kinds of detection methods. There's also the RST. Some of you may be familiar with its older name, WFIRST. This will be launched by NASA mainly for cosmology, but it is going to have applications to exoplanets with direct imaging and gravitational microlensing. And in particular, the RST is expected to dramatically improve our understanding of planets that are beyond the orbital periods that Kepler was able to see. So beyond maybe 500 days, it'll make a really big difference. There's also Plato. This is an upcoming European Space Agency mission that will use the transit method to find rocky planets in the habitable zones of different types of stars. And the James Webb Space Telescope, which some of you may have been following in the news. It was originally supposed to launch in 2007, and it has since been delayed several times. So I'm not sure when it will launch, but if it does, when it does, it'll be really exciting. JWST isn't really designed to be finding planets, but it will actually be able to tell us about the atmospheres of planets. The technology right now is not able to find different molecules in the atmospheres of small planets like our own Earth, but JWST may be able to find things like water or biosignatures in the atmospheres of small planets for the first time, which will be a really significant step forward in understanding the prospects for exoplanet habitability. So just to wrap up this talk, I'd like to summarize some of my last thoughts and takeaways. The first being that exoplanet hunting has really exploded in the last few decades. Again, the first exoplanet was only discovered in 1992, and a few dozens were known by the turn of the century, and today we know of thousands. And with those missions that I mentioned, there are going to be tens of thousands of exoplanets expected to be discovered over the next decade. Our perspective of planets in the galaxy is also continuously changing. For thousands of years, the only planets that we knew about were those in our own solar system. And today we know of so many different exotic kinds of planets, and the fact that they have such an incredible diversity tells us something about planet formation and evolution theories. For instance, there were those hot Jupiters that I mentioned, Tatooine planets, a lot of other examples of diverse exoplanets. And finding more planets helps us understand what it means for a planet to even be Earth-like. Finding examples of these small planets in the habitable zones of stars has important implications for the search for life elsewhere in the galaxy. And what I really find incredible about these discoveries is that they've turned something that a few decades ago was purely in the realm of science fiction into something that is an established subfield of astronomy that spans planetary astronomy, chemistry, biology, statistics, and it is extremely fast-growing and relatively a new field. And one of the great things about planet hunting is that anybody can take part, whether you're an exoplanet scientist with a PhD or a member of the general public, you can actually make some really significant contributions. Thank you.
Thank you so much, Michelle. That's awesome. Yeah, we have a question here, and I might have follow-up questions for this. This one says, Michelle, thanks for your talk. Can you briefly discuss the statistical methods you use to come up with your candidate exoplanets? And I think that's related to my question, is somehow you found 21 planets that NASA did not find. Yeah, can you talk a little bit about your method, the statistics for finding those?
Sure. So just because there have been a lot of just because Kepler has released their data to the public, it's been a really popular source for independent searches. So I'm by no means the only person to have done this. The idea is when you're looking at these really, really small planets, especially those that are like the Earth, that have really long orbits, they're going to be what's considered a very weak signal. So the analogy that I like to give here is if you can imagine a crowded room and everybody's talking, it'll be really hard to be able to listen to the people who are speaking really quietly compared to the noise level of the room. And the ones that are speaking really loudly, shouting, are going to be really easy to hear. So even if you can, just small changes to a search algorithm can actually reveal a lot of new planets, different planets than another pipeline, just because the probability of missing these planets is so high. So there were a few differences that I had in my own pipeline. One was just the way that I set up the data. So before you search through the data, you have to clean it up a little bit and remove things like stellar variability. So the process that I used was slightly different than what Kepler did. The search algorithm I used was slightly different than what Kepler did. So I didn't end up finding as many planets as Kepler. So my pipeline was a little bit less efficient than theirs was. But just because these really small, weak signals are going to have a high probability of being missed, regardless of what pipeline you're using. Essentially, it was just a probability game of which ones that I would find and which Kepler wouldn't. And likewise, Kepler found a lot that I didn't as well.
Nice. I actually have a question too. So you mentioned Jason Rowe has posted his source code on GitHub.
Mm-hmm.
That sounds very technical. Do you have a software background or a statistics background, or can somebody who doesn't really know much about either get involved in this?
Right. So this is one of the reasons I mentioned the planet hunters, because it's you just have to look at pictures essentially. There's no coding required with that. In terms of going the route of looking at some transit code on GitHub or the internet, when I started my summer research experience, I didn't actually have any programming background. I didn't know how to use Python. I was really starting from very little knowledge. And so I did receive a lot of help from Jason, and as I mentioned, he has a lot of tutorials which were really helpful. If anybody is interested in going this route, it is going to take some learning if you're not familiar with the coding, but in the past I've offered to people, anybody can ask me questions about how I used his code and how I applied it. And I've actually written up some guides for people who've asked me just after these kinds of talks, like high school students, and help them to get started with planet searching as well. So I extend that invitation to everybody listening here. If you have any questions about this and are curious to know more, even if you don't have that much coding experience, I'm happy to help you.
All right, awesome. One more question. So this is from Lori Roche. She's asks, Michelle, are the graphs of the before and after Kepler planet data available publicly?
Yes, I think I cited, let me find them. So these are from a paper, this is from a paper by Natalie Batalla, which is on exoplanet demographics and essentially the state of exoplanet hunting at the time that the article was written. So she had this really amazing comparison of the before and after for Kepler.
That's awesome.
But yeah, I believe that's publicly accessible.
Cool. Well, excellent. Thanks again, Michelle. It's always fun hearing from you and seeing what you're up to. And we're very excited about your work, and I think from everyone at RASC, they're really looking forward to what you come up with in the future for us, especially with tests coming online.
Thank you.
Yeah, thanks a lot.